Okay, so this is section 10.1, and we're just going to do a little overview of it. It's not too bad. Hold on, let me flip back over here. And this is the three-dimensional coordinate system. Okay. And there's a couple of things that I read in the notes that you kind of need to know. You kind of took some harder classes before you took this. And this kind of explains what vectors really are. Okay, so you just need to keep in mind that vectors provide particularly simple descriptions of lines, planes, and curves. And what we do is we pretty much start talking about 3D figures instead of two-dimensional figures. So we add a whole other axis to the X and Y axis, okay? We will use vector valued functions to describe the motion of objects through space. Okay? We usually find a point on a two-dimensional space the XY coordinate plane and we label that point XY, and sometimes we label it AB. Okay, so just some generic number. So what we do is we take that XY plane and we're going to turn it three-dimensional, and we represent any point in space, which is three-dimensional, by an ordered triple ABC, which is, of course, X, Y, Z. Okay, so we have, and these are a little hard for me to draw because I didn't have to take that. I took Cal 3, but I didn't have to really take much more than Cal 3. Well, I did have to take university physics, but those were the only times I really talked about an XY, a three-dimensional plane, XYZ. Okay, so here's what happens. This can be, of course, this can twist around. This is my x-axis, and these are positive values, like 1, 2, 3, okay, because that's my origin. This is my z-axis, and then I have my y-axis, okay, and this is positive, 1, 2, 3, okay, and z, of course, is positive, 1, 2, 3, okay. So, and you and I kind of talked about this, that you can see this a lot better if you use the corner of a room. So like I'm in the bedroom right now and I'm looking at the corner of the room. And a three-dimensional representation, instead of having 4 quadrants, we have 8. Okay, so, and of course, they're not called quadrants anymore, they're called octants. Okay, so if I'm looking at the corner of the room, like where the left wall meets the right wall and that crease goes up to the ceiling, that's my z-axis. Okay, and the right wall, okay, the crease that runs from that origin down in the corner of that z-axis, that right wall is my y-axis, okay, and that's the positive y-axis. And the plane that's formed, like if I colored in the wall right there between the z-axis and the y-axis, so I'm talking about like here's z, okay, here's the ceiling up here, here's the floor, and here's another crease, and this is y, okay, and this right here is the YZ plane, okay. Now we also have this x-axis. Here's the other wall right here, okay. So this wall right here, this crease to the left is my positive x-axis, and this wall right here is my XZ plane, and the floor, this chunk right here, is the XY plane. Okay, now all of these are positive, okay, except when, and so that makes, we have these 4, and then it's kind of like if we had a floor below that, then you would see the other 4 quadrants. Like if you had a 2-story house and then you went below your floor, like if we were on the top floor, then there's 4 more planes under there, which makes 8. It's like having 8 quadrants, but quadrants are not the right word. Octants is the right word. Okay, so we're going to have a plane up top that deals with a positive y and a positive z, or a positive x and a positive y and a positive x and a positive z. And then below and behind, we have the negatives. Okay? Okay, so that and we had already kind of explained that. And I wrote a little note on that. This divides, the space into octants. 4 on the first floor, with the, let's say 4 on the first floor. We're not going to say that other part. Okay? Let's see what else I said. Oh, this is important. It's about a point. Okay, so they're going to give you a point, such as the point P of A, B, C determines a rectangular box. Okay? If we drop a perpendicular P to the XY plane, we get point Q. Okay, and this figure is actually on page, let me just a second. It's either on page 537 or 538. It's one of those figures, okay? Because they're telling you how this actually makes a box. let's see, we've got, oh no, it's going to be on 538. 537 shows the corner of the room. Okay, 538 shows the point ABC, and it's showing you how to make the box to make the plane. Okay, point Q, where did I go? With coordinates A, B, 0, called the projection of P on the XY plane. Okay, you'll notice that Z coordinate is a 0 because we dropped that perpendicular down to the XY plane. So if we're sitting on the XY plane, then Z is 0. Okay, it's not going anywhere. It's like it's kind of like on the line kind of thing. Okay, R being 0 BC, where do you think that's going to happen? And S A0C are the projections of P on the XY plane. Let's see, that should be the YZ plane. That should not be XZ, sorry. That should be the YZ plane. And XZ plane, respectively. And I'm going to double check that, but with that 0 being X right there, that tells me that I'm in the YZ plane, and then with the Y being 0, that tells me I'm in the XZ plane. Okay? Yeah, YZ and XZ. Yeah, I was right the second time. Okay, so now we're going to get to some examples now, and I know you don't like talking about the stuff in the beginning. I really don't either. I kind of like to get to the problems, but this is not math that we are normally talking about, okay? Cal 3's like that. We're talking about 3 dimensions now. We're not in our normal XY plane going on, okay? So let's look at example 1. What surfaces, excuse me, I'm sorry. What surfaces in R cubed are represented by the following equations? Okay. A, Z equals 3. Okay, well, if Z is 3, Z always has to be 3. Well, all right. What are X and Y then? Well, X and Y can be anything, just as long as Z is 3. So what we get is the set X, Y, Z such that Z equals 3. Well, what does that really mean? I just wrote some stuff down. Well, what it is it is the plane that is parallel to the XY plane running through Z equals 3. Okay? So pretty much what you're doing, here's Z, there goes X, there goes Y, Okay, this is Z. I go up to 3. All right, and so you're making this plane that runs through here. That is now, let's see if I can draw it. I'm not sure if I can or not. It's got to be parallel. Not bad. I never was good drawing the uh, like floating in 3D space here kind of drawing. This actually goes in the back some. Hold on. Because you got to make it look like it's running through there, okay? So if I had, and it goes through this space right here. It is now parallel to this bottom plane right here. Okay, and this is what plane is this? Well, that's the XY plane. And see how this floats? This is darker. This should be a little bit lighter here. It's kind of like, okay, see, it's like you see, can you see? That's like at 3 there. 1, 2, because this is underneath there. And that plane floats above. It's parallel to that XY plane. Okay, so let's talk about what B says. B asks, what's represented by y equals 5? We're going to get the same kind of thing. We have the set xyz such that y equals 5. Okay, so this time, here's my z. Let's see how I can do here. Like I said, I'm just going to apologize. I'm not the greatest at this. I didn't take enough classes to practice. I took Cal 3 and 4, which dealt with that, but evidently it wasn't enough. Okay, so we're at y equals 5. Well, 1, 2, 3, 4, 5. And it's going to be a vertical plane that is parallel to the xz plane. Okay, here's x, here's z, here's this plane. See how it sits up tall? Well, so this one is going to run through there. If I were to make that a plane. So this one is going to run through there also. See how it sits like that? This comes out. This is going to be a little bit hidden. Okay. And see how it's running through 5. There's 1, 2, 3, 4, 5. You can probably see it better if it's lighter. See how it cuts it? I'm saying it cuts right there. And then they both stand up like that. Okay? So it is the set XYZ such that y equals 5. And it is the vertical plane that is parallel to the XZ plane having y values of 5. Okay? So not too bad. Okay. Oh, I did not realize that. I'm not sure what this is. Change template. Squared paper. Apply. Apply change. Okay. Make sure your paper's still there. Yep. Okay. So in general, we have a few notes here. A few more notes before we move on to the next example. In general, in our 3D coordinate system, our 3D plane here, XYZ plane, we've got x equals k, where k is a constant. So like we saw up there, like x equals 3, y equals 5. is a constant, where K is a constant, represents a plane parallel to the YZ plane. Okay, so you'll notice a pattern here. We have X equals a number that's going to be parallel to the YZ plane. So let's think about it. If I have Y equals a number, okay, what am I going to get? Of course, where K is a constant, represents, what's it going to represent? What do you think? It represents a plane parallel to the, which axis? Well, which plane? Well, you guessed it, XZ plane. Okay, and then of course, if we have Z equals K, where K is a constant, represents a plane parallel to the XY plane. And Tony, honestly, when we get up to Cal 3 like this, you've kind of already learned the nitty gritty part, and Diffie Q will be a lot easier too once you can start seeing. And Cal 3 is kind of like seeing, because you have vectors and now you're talking about spaces and three-dimensional things, and it's not as strange, honestly, as all the algorithms and the theories and everything you have to memorize in Cal 1 and Cal 2. And now we see it and then we just apply it, in which we can get through that. So it's going to be good. Let's look at example 2. Okay, we want to describe and sketch the surface R cubed represented, that just means in a three-dimensional plane. That's all that R cubed means. By the equation y equals x. Okay. Well, you know, y equals x is normally just linear. And so when x equals 1, y equals 1. When x equals 2, y equals 2. That kind of thing. Well, it's still kind of the same thing. Okay? If we write it like we did on the set earlier, we can say the set. But this time we can say, since y actually equals x, I can say x comma z. Because whatever I pick for x, that also has to be y, right? Because y depends on x here. Such that x is a real number. X is in R. And z is in R. And that just means they're real numbers. That's all. That R stands for the real number system. Okay, so what is it going to be? Well, you know it's going to be a plane. So here's what we kind of have. We have z. Of course, there's my z. And there's my axis. There's my z-axis. This is the positives of them. This is the y. And you know, and that's the positive, you know, normally it will be some kind of line that goes like this. Well, that's what it is. Okay, but it makes a plane because you can have z equaling kind of anything. So what you have, hold on, I'm sorry. Is you have this, it doesn't have to go like that. I was doing pretty good there, sorry. Let's just keep going. Okay, so here's my plane, because here's xy. This is y equals x. Okay, so here's my plane. Can you kind of see it sitting out there? I kind of need to erase that y a little bit. And then you're going to see it sitting there a lot better. Actually, you'll like this a lot better, and you'll be a lot better at it because you could draw, and I never could draw well. Okay, so this is a vertical. It kind of stands up. It's like we draw the line y equals x with that x in that x and y plane, and then we go up and attach back to the z-axis to make this vertical plane. It's like we're putting up a wall in a house. Okay, this is a vertical plane that intersects the xy plane in the line y equals x and z equals 0. Okay, because here's y equals x. This line right here is y equals x. And where is it hitting? It's hitting at the origin. What's at the origin? Z, what is z at the origin? 0. Okay. All right. Distance formula, I'm going to go ahead and write it down. It's nothing new. It's just now you have a z in there, whereas before we had x's. Given P1 is x1, y1, z1. Okay, and I don't think I said that right. Usually the distance formula just deals with x and y. Distance formula is the same thing, except now we have x, y, z. Sorry, I was thinking about something else while I was talking. X2, Y2, Z2. I've got a cough, sorry. And P3 is X3, Y3, Z3. Okay, so we need to be able to, we know the distance from, oh, we don't need P3, I'm sorry. Oh my, I need to think a little better. Read my notes. The distance between P1 and P2, we're noting that with, it looks like absolute value bars. It's just saying the distance between it. That's what's used to denote that. Nobody may have ever told you that. X2 minus X1 squared plus Y2 minus Y1 squared plus Z2 minus Z1 squared. Okay? So example 3, we have, it says the distance. We want to find the distance from the point P to negative 1, 7 to the point Q 1, negative 3, 5. Okay? And it says is because you're now supposed to tell them. So all I've got to do is I do the square root of x2 minus x1, so 1 minus 2 squared plus negative 3 minus negative 1, so plus 1 squared plus 5 minus 7 squared. That's going to give me the square root of negative 1 squared is 1, plus negative 2 squared is 4, plus negative 2 squared is 4. That gives me the square root of 9, which equals 3, of course. Okay? Okay, I'm going to kind of skip example 4. You're proving what, in example 4, you're proving the equation of a sphere. And I'm just going to give you the equation of the sphere. So I've got equation of a sphere is, and then we get a little definition, an equation of a sphere with center C, which is HKL, and you're accustomed to with the center of a circle being HK. That's not unusual for you. Well, it's the same concept. We just have an extra point because we've got that z. And radius r, like always, is, well, usually we have x minus h squared plus y minus k squared equals r squared, right? Well, this time you got to have that z, so plus z minus l squared equals r squared. So example 5, and I think I can fit it in down here, says show that x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0 is the equation of a sphere and find its center and radius. Okay, so you're going to have to use, you're going to have to complete the square here. So I write down the equation, and then remember, you're going to have to complete the square for the x's, the y's, and the z's. And so if you'll remember, when we complete the square, I'm going to go ahead and I'm going to move that constant, that 6, to the other side. So minus 6. I'm going to put the x's together, and then, well, I should have done that to start with. Hold on. I need to save this space here. I thought I was just rewriting. Okay, so you got to get all the x's together. You got to get the y's together. You got to get the z's together. X squared plus 4x. Okay. Then I have plus y squared minus 6y plus z squared plus 2z equals negative 6. Move that 6 to the other side because you got to have a radius over there anyway. Now we're going to complete the square on the x's, the y's, and the z's. Well, that's going to become x squared plus 4x. Remember, take half the 4 is 2. Square the 2 is 4, so plus 4. You just have to remember that over here with the negative 6, if you add 4 on the left-hand side, you have to add 4 on the right-hand side. Then I have y squared minus 6y. Well, half of 6, negative 6 is negative 3. Negative 3 squared is 9, plus 9. So I have to say plus 9 on the right-hand side. Then I have plus z squared plus 2z. Half of 2 is 1. 1 squared is 1. Now you factor. Remember, these become perfect squares. So if I factor x squared plus 4x plus 4, I know that's x plus 2 times x plus 2, which of course is x plus 2 squared. Plus, well, that's y minus 3 squared, because that's really y minus 3 times y minus 3 when I factor it. It's what's called completing the square, because you want to make it a perfect square. Plus z plus 1 squared equals, oh, I forgot my plus 1, is going to equal, let's see, negative 6 plus 4 is negative 2, plus 9 is 7, plus 1 is 8, equals 8. So I have a center at, and remember, the equation up here is, these are x minus, y minus, z minus. So we're going to change, we really need all those to have been minuses. So how do we compensate for that? We change the sign. This would be like x minus negative 2. So we have a center at negative 2, 3, negative 1. And we have a radius of square root of 8, which is really 2 square roots of 2. And how I got negative 2, remember, this is really x minus negative 2 squared plus y minus 3 squared plus z minus negative 1 squared equals 8. That's where it has to be in the form, in this form, okay? And that's where the negative 2, so you have the minuses, that's a positive 3, of course, and then that's a negative 1. That's why we changed the sign on that. And that's it for the lesson. I'm going to go ahead and post this and tell you to watch it, and then I'll get started on the homework.